B.3 Horner's rule. That's the method, smart method we mentioned before, Horner's rule. Okay? Yeah. Because this method is important. So there is a name for it, Horner's rule. Okay, let's see what's the rule here. Okay, all right. So here, key to the success, factorization. Okay. Yeah. So we should push very hard when we apply factorization technique. As hard as we can. In other words, we should use factorization as much as we can. How about that? That's good. Yeah, scary. Yeah, but the effort, the rewarding of the effort is big. Yeah. The strategy for generalization, another strategy. Okay? Yeah, so many strategies. Do factorization as much as we can. Our current strategy. As much as we can. Okay? How about that? Okay? Yeah. We know the reason we can do better factorization. So we should apply as much as we can here. Okay? Here, as much as we can, there is a name for it in algorithm, greedy idea, greedy algorithm. So this is the greedy idea. So there is a type of algorithms we call greedy algorithms. That's in chapter 8 of the textbook. Very late, chapter 8. Yeah. But I want to bring it here. Yeah, because for this class, we may not have chance to cover chapter 8. Yeah. But there are a few places we can apply the greedy idea, greedy approach. So this is the first place we can apply that greedy approach. Okay? So when you have some special method, we want to apply it in some sense. In what sense you need to specify? In some sense, as much as we can. That's the greedy approach. Okay? The algorithms, we call it greedy algorithms. Here, we use the greedy algorithms here. Let's do the work. When we do the work, I like to do another experiment where n equals 3. So we do another experiment to get a little more experience. Yeah, because when we have one more term, can we, this time using the greedy strategy to apply factorization, another round, more. All right, yeah, so let's try. Okay. The factorization should cover as many terms as possible. No. Here, we cannot apply factorization on all the terms, right? Because there is no common factor for all the terms. All right? But if we ignore the first term, then we have a common factor, right? After we ignore the first term, the remaining 3 terms, there is a common factor. So we can apply factorization. How about that? So that's the meaning. We apply factorization to cover as many terms as possible. One greedy, so here also the greedy way. Okay, cover as many terms as possible. One greedy definition here. Okay, yeah. Then our first factorization looks like this. So we factor that common factor x out inside the parenthesis. there are 3 terms inside the parentheses. Tell me, what's the next step? When you see this expression, what do you want to do next? Greedy strategy, do you have another chance to apply factorization inside the parenthesis? Another round factorization. Yeah. After you ignore the first term inside the parenthesis, you have common factor situation. So you can apply factorization another round. Okay. So for the remaining terms, do this factorization, you will get this expression. In this way, we push the factorization as much as we can, right? Very hard to the end. Because after this, we cannot do further factorization. No further factorization can be done. So we have to stop. Okay? That's the best we can do. That's the essence of greedy strategy. Greedy approach, that's the essence of it. Okay, all right. So now we are satisfied with this expression. Question, can we do the same thing for the general n? Our destination, we need to work on the general polynomial with degree n, degree n, do the same type of factorization. We can, right? Not too hard, right? Using the same pattern here. Using the same pattern here. Push to the general case with the same pattern. Can you see this expression? For the general case, can you follow that? This is the so-called Horner's rule. If you calculate a polynomial in this way, it looks strange, right? Looks, not normal. Yeah. That's the so-called Horner's rule. Horner's rule. All right. What's the benefit of this way? What is the benefit? Now, I ask you, count the number of multiplications in this last equation, last polynomial expression. Now you count the number of multiplications and tell me that number. Counting number. Counting number. Can you apply the method I introduced before, counting by reference? Counting by reference. And that's correct. All right. The first multiplication is here, right? The first multiplication is here. Can you associate with the subscript 1 here? Second multiplication, the parenthesis with the subscript 2, and so on. Okay? Yeah. So this Horner's rule, we apply counting by reference. Multiplication, the last one associated with n. You count the subscripts from 1 through m. That's n. Okay? Yeah. Counting by reference. Question? Yeah.
So why wouldn't it be n plus 1?
Yeah. Right. The first one, you do not do multiplication, right? Yeah. Multiplication, when you have a pair of parentheses, you do multiplication, right? But the last multiplication, you do not have pair of parentheses.
I was saying that because it's inside the parentheses.
Right. Inside. So here, we associate each multiplication with a subscript number. In that way, subscript number. In that way,
third one is to do with N.
Right, third one, X inside that, X3 plus something.
I get it. Okay.
Yeah. Now you should appreciate the counting by reference, right? No? Because this one is harder. If you do not do that one-to-one correspondence, one-to-one association, it would be hard, right? Not that straightforward. But if you discover that one-to-one correspondence relationship, it's not hard. Not that hard. Okay, all right. Yeah, I hope you get it. And multiplications. Now we need to see how good is our new algorithm. This is a new algorithm, Horner's rule. The number of additions the same, still n, right? We do not reduce the number of additions, but we reduce the number of multiplications. Okay, yeah. So let's look, yeah, we have that, and yeah. So we need to do the last round analysis to see how big is the improvement. How big is the improvement? We want to see that. Is that improvement big or little? We want to see, we want to get some impression of that. Okay, yeah. Multiplication reduction. Let's see the multiplication reduction from the number. So here, let's consider the number of multiplication, that reduction. Okay, now. Old method, this many, 1/2 times n plus 1. Old method. Horner's rule, new method, n. This reduction. Can you see? Definitely you can see the difference, but how big is the difference? Can you see that? How big is the difference? Can we say that's a big improvement? Big improvement? Super big improvement? Yeah.
It's like about 50% improvement, right?
I mean, so it's an exponential one, right? Like the more ends you have, the bigger the difference.
Good. But he said 50%. He said something 50%. Is that a fair number, fair description? Only 50? Only 50 improvement? Can we say 99% improvement? Is it a fair number? 99% improvement? How do you feel? Do you think, you know, so we want to see how good is the improvement. Can we say we comfortably get 99% improvement? If it's a fair statement or not, 99% improvement.
But yeah, at a certain point, I feel it's probably going to be a 99%, depending on how big n is.
Yes, yeah, how big n is. When n is small, we don't have 99%, right?
Right.
When n is large, do we have, when n is very large, do we have, n is very large, do we have 99% improvement?
Yeah, I mean, like, when we were looking at the
Yeah.
work for like polynomial like 3, it was already a 50% because the original took 6 multiplications and the new one's 3.
For our algorithm, so we only worry about large n. We do not worry about small n. So the concern always when n is very large. That's our concern. When n is relatively small, we don't worry. Our computer is super fast. So we never worry about when n is small. Only when n is very large, then we really need to see how well our algorithm performs. Okay, so you can assume, let's say when n is sufficiently large, can we say that? When n is sufficiently large, we have improvement at least 99%. Is that a fair statement? Actually, it's a modest, too modest. 99 is not big enough, too modest. Too modest. Not strong enough. Not strong enough. All right. Yeah. In order to convince you, yeah, here, I want to convince you. How big is the improvement here? Our last 10 minutes, we have final 10 minutes. I want to convince you how big is the improvement. Okay, bigger than that, 99%. When n is sufficiently large, there is this. Yes. All right. Let's see. Let's do some experiments to see that difference. All right. Impact of multiplication reduction. This is the reduction, but we need to plug in some numbers to see the impact. All right. How do we visualize the improvement? We want to feel about, visualize. Because when we look at these formulas, it's hard to visualize, right? In our mind, how do you visualize these two different formulas? You cannot. But if we change to some concrete quantities, then you can visualize easily. Here, I want to convert it to some easy quantities in your mind, so you can feel about those quantities. I know how big they are, so you can get an idea. Span, yeah, but I need to, yeah, put in the airplane, but only 10 minutes. Yeah, I hope. Let me just, yeah, all right. Yeah, visualization, okay? The last step, visualization. Let's work on some examples. Let's plug in two special n values here. Okay, the first one, n equals 1,000. Can we say sufficiently large here? N equals 1,000. They're very large, but think about we're in a big data era. Okay, big data era, that 1,000 data items, not that big. People talk about millions, billions data items. That 1,000, very small number. Okay, yeah, our first example, we work on this relatively small number. All right, yeah, plug in right-hand side, just 1,000. What is the left-hand side? I use approximation. In may not be precise. Okay, yeah, approximation. Yeah, all right. 500,000. 500,000 versus 1,000. 500 to 1 ratio. Think about 500 to 1 ratio. Is it better than 99%? Think about that. It's better than 99%, right? Much better.
I feel like you reached 99% around like 135.
Yes. Yeah. So that's why I say, too modest. But you may, at the beginning, you may feel I'm too aggressive, right? Yeah. The estimate, too aggressive. Yeah. All right. Second, let's try second. This time 1 million. N equals 1 million. All right. So this time, right-hand side, 1 million. How big is the left-hand side? Plug in. Still approximation. How big is this number? Can you read that number using appropriate?
Half a trillion. 500 billion. 500
Trillion?
half a trillion.
Yeah. Half a trillion. Yeah. Yeah. He said half a trillion. All right. Yeah. Here. So million, billion. So 500 billion. Yeah. Half a trillion, good, half a trillion. Half 1,000 billion, because 1,000 billion, that's trillion. Half 1,000 billion, 500 billion. Yeah. The ratio, let's look at the ratio here. 500,000 to 1 ratio. 500,000 to 1 ratio. All right? Yeah. Now you believe the difference is huge, right? The difference is huge. Not, but you didn't realize we are in the big data era. All right? Big data era. So you can imagine the amount of data we may need to handle every day. Okay? Yes. So many big servers in the world, cloud computing, you know, you can imagine. All right? Yeah. Then the last piece of the story, the final 5 minutes, I still push another step forward. Last piece. All right. We need to get a concrete impression here. I want to give you another story piece, concrete expression. Suppose we run these two different algorithms on the same machine in a real world situation, right? So you provide business solutions to your customers, okay? Suppose you have two different solutions. Old one, the first one, yeah, you get a response time corresponding this 500,000 time units. Then the improved one later, so you try very hard, you find a much better solution, and the response time is 1 time unit. Okay, now you solve the same problem. Here, let's just assume 1 time unit corresponds to 1 second. How about that? 1 second, you know how fast it is, right? So when you use the new method, you hit the enter after 1 second, your customer can see the result. That's the second method. 1 second after you hit the enter, result on screen. Okay, yeah. Think about how happy your customer are, all right? Yeah. Now, let's look at the first method. After hit the hand, enter, how long your customers need to wait. We use second time unit. 1 time unit is the second. Okay, all right. Then you need to wait 500,000 seconds. How long is that? Let's do the conversion. How many days? How many hours? Let's convert to that number. Okay, 5.8 days. If you do conversion, you'll get 5.8 days. Close to 6 days. Think about that.
Go on vacation.
Yeah, think about you bring the solution to your customers. Well, you hit the button. Your customer, they need to wait for 5.8 days. Think about that. Right? Can you imagine that? But the second solution, I think the first one, you won't bring the solution to customers, right? So you don't want to embarrass yourself, right? But the second one, you will be very happy to bring that solution, right? The second solution. Think about that. You're very happy. 1 second. Okay? Yeah. So through this example, I try to let you feel for this class, after we learn all the knowledge, all the techniques, we have a chance to do this big improvement. Okay? Yeah. Ordinary way, the slow, but use some smart way, we can get this big improvement. All right. So that's the part B.